Now we're going to talk a little bit about the physical properties of alcohols. And specifically, alcohols have unusually high boiling points compared to other organic solvents or organic molecules. And the reason is because, like water, alcohols have an OH. So the same way water has H and OH, alcohols have some carbon group and an OH. And this allows alcohols to hydrogen bond. And that's a very strong intermolecular force. So to review intermolecular forces, as the intermolecular forces between molecules increase, the compounds will have a higher boiling point. So what are intermolecular forces? Intermolecular forces are non-covalent interactions that hold molecules together. Okay, and this doesn't mean what's holding one hydrogen to an oxygen to another hydrogen in a single water molecule. But for example, if you have a glass of water, what's keeping those water molecules from immediately going into the gaseous state? What's the intermolecular forces between one molecule of water and another molecule of water and another molecule of water and so forth? Those forces are non-covalent, they're not bonds, but they are interactions that hold those molecules together. We have three primary types of intermolecular forces. We have van der Waals forces, dipole-dipole interactions, and hydrogen bonding. The van der Waals forces are also sometimes called London dispersion forces. Now with these three forces, they're actually going from left to right in increasing strength. So van der Waals forces are the weakest. Hydrogen bonding forces are the strongest. So let's review what these three forces are. So the first, the van der Waals forces, these exist in all molecules. And these are essentially very slight temporary dipoles that are existing even in compounds that we don't think about having dipoles. For example, if you have two molecules of butane, at any given time, there's going to be some electron polarization in this chain to give alternating charges. And then a second molecule at any given time may have the opposite alternating charges. And what this results in is these two molecules kind of being attracted to one another. So what you can see is that the longer the chain or the more surface area you have here, you're going to have stronger van der Waals forces. So this increases with surface area. Longer chains are going to have better van der Waals forces. And then you can imagine if you have a bunch of branching in a molecule, that's going to disrupt the alignment of these, which is going to disrupt the van der Waals forces. The next are the dipole-dipole interactions. These exist in molecules with a permanent dipole. So this is similar, but now we have a permanent dipole. So for example, if you have a Cl in a molecule, we have a permanent dipole here, which gives delta minus charge to the chlorine, delta positive to the carbon. So what this can do is align with the dipoles in another molecule. So now if I draw another chloropropane, you can see how the opposite charges here can attract and give us a network of dipole-dipole interactions which help hold those molecules together. The last is the hydrogen bonding. So this exists in molecules with OH, NH, or FH. So what this is, if we just look at the simplest case of hydrogen bonding, water. If we draw a couple of water molecules, what will happen here is a lone pair on one oxygen will be attracted to the hydrogen that's bonded to another oxygen. So that's a hydrogen bond right there. Here's an example where we're given 4 molecules and we want to rank these from the lowest expected boiling point to the highest expected boiling point. So what you really want to do is identify the intermolecular forces that are present in each. So each of these have van der Waals forces. The next thing we can identify are dipole-dipole interactions. So which of these have permanent dipoles? The chlorine has a permanent dipole. The one with the oxygen has a permanent dipole. So these two have dipole-dipole interactions. And then our third intermolecular force is hydrogen bonding. And only the one with the OH has hydrogen bonding. So based on this, we can already start to make an arrangement. So we can say that this molecule with the OH has the most intermolecular forces, so it's going to have the highest boiling point. So let's put it at the top of our list. And that will be followed by the molecule with the chlorine. But now we're down to these two compounds that only have van der Waals forces. So how can we figure out the difference between these two? Well, the one on the top has a 4-carbon chain. The one on the bottom has a 3-carbon chain. The longer chain has more surface area. More surface area means stronger van der Waals forces. So you would expect butane to be higher boiling than propane. Just to give you an idea of the magnitude of this effect, going down from propane, it has a boiling point of negative 42 degrees Celsius. Then just adding that extra carbon brings it up to negative 1 degree Celsius. Adding the dipole-dipole interactions, now we're talking about something that is liquid at room temperature, 46 degrees Celsius. And then the OH with that hydrogen bonding brings the boiling point all the way up to 97 degrees Celsius.